Arshiya. I'm a PhD student in the Mechanical Engineering Department at University of Washington in Seattle, and today we're going to talk about combustion and how I use HPC to model emission. There's no explosion, so don't get worried. Just to get started, this whole thing broke. Okay, just to get started, let's start this presentation with a question for you, okay? In the US, not in Europe, in the US, how many percent of the energy comes from burning fuel? What do you think? 70, 80, right on. Despite the growth in renewable energy the past few decades, unfortunately we're still using a lot of fuel to produce power, for power generation, for transportation, in industrial purposes, and so on. A report in 2015 showed that U.S. is importing about 9 million barrels of petroleum per day from 88 different countries. So we're using petroleum quite a bit in the U.S. When we're burning fuel, we have emissions that can cause global warming. So it's really important to study combustion, to study emission, and reduce them, hopefully. Okay, as I said, petroleum plays a very important role. One part of my research is to study renewable fuels, the kind of fuels that we can get from animal fat, from camelina seeds, from forest and farm residues. We can turn these fuels into, we can turn these renewable sources into fuels that we could use, for example, in airplanes, okay? So, and that's the main purpose of my research. I study jet fuels and renewable jet fuels. As you know, when we fly an airplane, we use a gas turbine to create a thrust. Air comes into the combustor. It goes to the compressor, takes its pressure really high. We send this high pressure fluid to the combustors, and the hot gas fluid has a lot of energy, goes into the turbine and creates a thrust in the airplane. If you zoom in on a combustor, you can see that the fuel and air comes in the combustor. It goes through a recirculation zone where the flame is stabilized, and then it exits and goes to the turbine. My research, as you know, this geometry is very complicated. There's a lot of temperature gradients, there's a lot of species gradients. So for my research to compare different fuels, I use a jet-stirred reactor, which represents the primary zone, or this recirculation zone in the combustor of airplanes. Okay? The emissions that I study, I measure CO2, but one of the most important emissions is NO and NO2. And combined together, we call them NOx. And it's been known that NOx contributes to global warming. It's a greenhouse gas. It also creates acid rains. It can create ozone layer and smog on top of the big cities when there's a lot of pollution. And also, it's very bad for our respiratory system. Okay, so the goal is to study NOx with a jet-stirred reactor experimentally, and then we'll measure emission. We model emission. So this is a simplified version of the reactor. We make the liquid fuel into droplets by atomizing them. We add hot air to the system. Fuel and air mix very well, and they go inside the reactor. And once they enter the reactor, they go through a whole recirculation zone. Any particle entering will leave the system after 3 milliseconds. We measure the temperature of inside the reactor with a high temperature R-type thermocouple, and we also measure the samples from the inside the reactor. Okay. We work with different fuels. Some of the fuels are pure fuels, and the other ones are some of the renewable fuels that we talked about. For example, FD gas is made by Fischer-Tropsch process of natural gas. We have a gaseous fuel, we turn it into a liquid fuel, and we can burn it in our jets. The other type of fuels is HP tallow and camelina. They're made from animal fat and from camelina seeds. And alcohol-based jet is made from biomass. Last year, about this time, Alaska Airlines flew an airplane from Seattle to DC that contained 20% of this fuel. And ever since, a lot of other airlines have started blending renewable fuels to their system, and they've had successful flights. Okay, and we're also studying Jet A, which is the commercial fuel for aviation fuels. Okay, this is a little chemistry for you, but these are the pure fuels that we have and the types of composition that they have: normal alkane, isoalkane, cycloalkane, and aromatics. A lot of the renewable fuels that we just talked about, they have isoalkanes and a little bit of normal alkane. And Jet A is just a mixture of all the types of fuels. So going to the experiments, we're plotting NOx versus fuels at a temperature of 17 to 1900 K. And what the research really showed is that the renewable fuels produce about the same amount of emissions as the petroleum jet fuels. One renewable fuel that showed a lot of promising values is HP tallow. It's the one from animal fat. It had lower NOx, it had lower black carbon emissions, and it was very stable. So this is very interesting, but alcohol-based jet is more interesting in Seattle because we have a lot of trees. Okay, so moving on. This was just the experiments. We can't really look inside the reactor and look at the species, or we can't really see what's going on inside. So we need modeling to figure all that out. So this is the reactor, and we use computational fluid dynamics to model the fluid and the chemistry inside this reactor. So what we do, we just extract the fluid out of the solid, we divide it into millions of cells, and we want to study what's going on in each cell, okay? A nice study, and I use the SAR-CCM code from Siemens. It's a commercial code. One of the employees last month did a very good study on a large-scale gas turbine. He had about 600 million cells. He used the cluster in Stuttgart to do his work, and he showed that the software scales up pretty well. So if this dashed line is the ideal case for scale up, he showed that the software at cold condition or hot condition shows a very good level of scale up. So because of the limits that I have on the cluster, I only use 50,000 cells per core. That means 50,000 cells go to one core, and the simulation is happening at the same time on around 200 cores. Okay, so this is what the mesh looks like. It's very refined. It's really hard to see each cell, but we solve Navier-Stokes equation that govern the flow in each cell. We model it using Reynolds average Navier-Stokes equation or large eddy simulation. There are different ways of solving this equation. And then for chemistry, we really want to know a lot about the chemistry inside the reactor. So we use detailed chemistry. That means we have to solve a transport equation for each species. So if we have a lot of species, this simulation becomes very difficult. Okay. So a little about turbulence modeling. My favorite way of showing it is by looking at a picture, a beautiful picture of the quad at UW. The cherry blossoms comes in March. And you can see a lot of definition in this picture. If we think in turbulence studies, this is direct numerical simulation. We are directly solving the Navier-Stokes equation. But a simpler model is still get the most of the structure, the bigger structure, and really modeling the very smaller structures. And the other case would be running a RANS, a Reynolds average Navier-Stokes equation. We're averaging every single equation. We see a somewhat a blurry picture of how the flow would look like. The beauty of RANS is that it's very cheap. You run a simulation, it runs in a few hours, in a day. If you want to run a DNS, it can't be done yet on many of the flows. It's way too expensive. And LES lies in between, but still, it is still very expensive, unfortunately. But the thing is, we're adding some models. So DNS would be the most accurate. Going to RANS is the least accurate. Okay, so now let's see how this looks like with our case. Okay, a little more information about large eddy simulation. This is a little bit of theoretical, but we're looking at turbulence kinetic energy versus the size of the eddies. If you ever looked inside the river or looked at the river, you see a lot of swirls in the river, and they come in all different sizes. And this is exactly what it is. In a fluid motion, we have different eddies. And with large eddy simulation, which is getting a lot of attention right now in industry, we're capturing all those big eddies, and we're letting those smaller eddies pass this filter and remodel those. Okay, so if we resolve the mesh very well, we're resolving most of our turbulence kinetic energy, but we're modeling just a small amount. Okay? Just talking a little bit about the computational cost of running large eddy simulation. We have a Lenovo cluster on campus that we can use. I'm limited to using just 6 nodes or 168 cores, unfortunately, but with this, if I want to model hydrogen, which is the easiest fuel to model on planets, I would have 10 species, and it would take me 3 months to get enough statistics of the flow to have enough information, basically. If I run methane, which is basically natural gas, it would take me about 6 months, and that's still running, so I don't have any data on methane. But if I wanted to model jet fuel surrogates, everybody would tell me you're crazy because it would take 8 years. I would never graduate. Okay? So for that reason, I'm going to focus just on hydrogen to tell you, just motivate why we need more computational power now. Okay. So looking at the reactor, just looking at a cross-section of the reactor, we have cold fuel and air coming in. They start burning, they recirculate. All these hot gases come back, and they mix in with colder fuel and air, and then they exit the reactor. It's important to look at O radical, because O radical is the main radical that creates NOx and emission. So this guy comes in, and it seems like we have a dome with high radical of O inside our reactor. Let's look at what happens if we do a large eddy simulation. Now this is a transient problem. We get a lot more detail about the structure of the fluid at the jet and in the recirculation zone. We can see these eddies rupturing from the jets, and here you can see that the dome doesn't exist anymore. It's really pockets of high O radical that's dissipating in the jet-steered reactor and in the recirculation zone. And so the beauty of doing this is that I can pick any point here, and I can get some statistics of the flow and see how the emissions look like. And this type of simulation is becoming very popular in industry. They're really trying to increase the cluster power to be able to run simulations like this, but we'll talk about that later a little bit. Okay, so comparing RANs to LES, if we measure the temperature from on this line towards the center line, going from 0 to 12, you can see that experiments showed that there's not much temperature gradient. Temperature is constant. But when we ran RANs, it showed that temperature drops where the core of the jet is, meaning that it predicts that the jet is longer. This would be terrible for industry. It would mess all their design. But when we ran a large eddy simulation, it showed that it basically captured the right trend. So that's good. But at the same time, RANs for this simulation takes 2 days versus LES that takes 3 months. So right now in industry, RANs is the common model used. I was doing an internship last summer in Siemens for their large gas turbine, and they would make a design of 1,000 designs about the angle of how air comes in, and we would get results in a week, right? But if we try to do this with large eddy simulation, each simulation would take months. So an industry really wants to move to large eddy simulation. That's why they're improving their clusters. They've started using cloud computing to be able to use LES because they know they can get better designs. They can decrease the emissions. Okay, and finally, we were just talking about hydrogen, and we looked at temperature and the radicals. What about jet fuels? We can look at this CFD simulation, a very expensive CFD simulation, and we can make a one-dimensional model that can run in seconds. So we look at this flame and say, okay, there's a flame brush, there is a shear layer, and then there's a recirculation zone. So we create this 4-element model that can run in seconds, and we can solve thousands of species using this model and say how much the emission is. So that's the beauty of it. So finally, I'd like to thank Lenovo for giving me this opportunity to come here. I've learned so much from every single booth here, and also the HiRack supercomputer system for letting me run my simulations on the cluster. All right, if you guys have any questions, I'll be right here. Feel free to come ask questions.
Ladies and gentlemen, Arshiya. Thank you, Arshiya.